Okay, well, thanks very much for the invitation to talk about this project. It's a project that's underway. In fact, it's a sort of a collaboration. Actually, I'm from the atomic molecular optical physics group, and Rob is from the high energy physics group. Okay, thanks. From the high energy physics group, and actually this project originated because of this community and a meeting with this community several years ago, actually via Marcus Arndt, I think, who said, well, you want to do these experiments. Peter Barker's doing experiments with cold atoms. Perhaps you should talk. So our department is something like 80 academic staff, and we had been there for quite a while and never spoken. So now we've spoken, and we have formed a research activity on this and others, as you'll hear from Rob very soon. Okay, so what I'm going to talk about, really, you've heard over and over again, so I'm not really sort of going to go through this too much, because what we really want to do is to recast this experiment that was done by Steinberg's group, done with photons, into using an atomic system and using atomic polarization. And so because I've seen this slide quite a few times today, I'll go over it very briefly, but it's important in terms of how to compare it to what we're working on. And so essentially, the essence of this is it's essentially a two-slit interference experiment whereby this calcite crystal is used to make a weak measurement, and the pointer here is the polarization of the light. And this calcite crystal essentially creates a phase shift on these polarization components, which now enable you to make a weak measurement of the transverse momentum, which we've heard about. And then essentially, by looking at how that is encoded in the intensity of these two polarization components, you can essentially work out a trajectory through the system between the slits and the detector where there's a strong measurement. So, and of course, so they saw these trajectories, and of course there's the link to bone momentum, which you've heard about today, so I won't really go into that and really talk about what we're doing and plan to do. So the idea really is to essentially just replace the photons here with atoms, and in our case, metastable argon atoms, and I'll explain why that is the case. And to do a similar double slit experiment and to have a weak stage somewhere in here, which I'll talk about soon, and to measure then, essentially make a strong measurement of position of these atoms as they fall onto the surface. And this measurement sort of describes the type of atoms that we're using, or describes why we use the atoms. So the general scheme is the same. So you essentially start off with a cloud, in our case, of cold argon atoms. So this is something that we had in the lab that was used for some cold molecule experiments. And the idea here is that you essentially, so this is J equals 2 total angular momentum. So in a magnetic field and using circularly polarized light, you can spin polarize this and make a polarized atomic source of atoms. You send it through a grating. You then have a weak stage here, which is, in our case, magnetic field that is tilted at some small angle, and I'll talk about that soon. And then some type of analyzer, for example, a Stern-Gerlach wire, or, as I'll show you, an optical field. And then the idea here is that we can, because we're using these argon atoms, which I'll describe soon, we can see essentially a single atom at a time arriving on this MCP, as you can, for example, with an experiment with photons. So just a quick thing. So as I said, the argon atoms have a total angular momentum of 2, which means there's 5 Zeeman sublevels in the ground state, which can be equally populated. And what we we essentially, we have an option to do this or not. in the source that we have, it's unpolarized, but we can apply a circularly polarized beam, and we can pump to this, it's called a stretch state, to +2 or -2, depending on the polarization of the magnetic field. And so we start off with this sort of like a plane wave here in this m=2 state. And this is analogous to essentially starting off with a linearly polarized light beam, except it's a kind of like a linearly polarized atomic beam. Of course, polarization is a bit more complicated because essentially there are 5 states rather than 2, horizontal and vertical. So the essence of the process, though, is this weak stage, which is essentially, so we have these different magnetic sublevels, or 1, depending on whether we put it into m=2 or we create a superposition and we put them all through this stage. But essentially, each magnetic sublevel experiences Lamore precession, and so what you see is a phase change, and this is the weak measurement. So if this phase change is very small, then this is our weak measurement with the strength given by these quantities here. And so this is very analogous to the calcite crystal. The only difference here is that we tilt this magnetic field here at a slight angle, such that if the particle comes through with this trajectory, which has a momentum in this direction or in this direction, you can see that it goes through different lengths of this magnetic field, and so accumulates a different phase. And that's how we essentially map phase onto, or map transverse momentum or velocity onto phase. Okay. So what would this evolution through the weak stage like? So we start off, for example, if we wanted to, in this state with m=2, if this is moving fast enough through this and the field direction, there's a rapid change in the field direction here, then we project into all of these magnetic sublevels with these probabilities. And then as this wave function progresses through the weak stage, then you accumulate this phase, like this Lamore precession that I was talking about. And this is what we're interested in. And so this is velocity dependent, so dependent on the transverse velocity, and this is what we want to measure. I should say when it actually leaves again, you get another rotation and another projection such that this phase can end up even in the m=0 state. So, and finally, so how would you measure this phase change? So what we can do is we can look at potentially at each of these M states by simply putting a current carrying wire there and having a non-uniform magnetic field, and then separating each of the M states out. And so unlike the Cox's experiment where you have, for example, you have 2, then you could potentially have 5 here, which of course is good in some ways, but it's also it means your signal is distributed across the MCP. Another way, of course, is because I said that there's some of this phase information now in m=0 when it leaves this magnet here. What you can do is actually use the linear polarized beam, which essentially, and I'll explain this a little bit later as I start talking about the experiment, in that it quenches out, so it takes out all of the components except m=0, and so you can make a measurement on that. So what would this look like? So for example, if we look at an interference pattern, this is some, I think 20 centimeters away from a double slit. If you have no weak stage in there, you get the standard interference fringe. And for example, if I look at one of these M states here, then you can see that there's a modulation in this intensity. And this is where this transverse momentum is now just in the same way as the photon experiment is encoded in the relative intensity variations. This is theory, yes. Yeah, that would be a really good experiment. I could only dream of such things. And of course, then what you could do is then construct a map of these flow lines. The difference is, I mean, what you realize actually in these experiments is, and maybe why Ephraim does things with optics, it's much easier in optics. So what you have to do in this case is you need to take the weak stage in the microchannel plate and you need to translate them through the experiment, which with optics, you don't have to do that. I mean, you could in principle do that with atom optics, but that just complicates things even further. So this is our experiment. So this is the experiment, part of this experiment that we had existing. So we put in, we take our regular argon gas, relatively clean argon gas. We flow this through a coil, and you essentially get not a neon sign, but an argon sign, and 1 in 10,000 of those are in this metastable state. And I'll explain why we want to use this particular metastable state. And then we can shutter this and we can send a beam through. We actually use laser cooling to cool this from about 400 meters per second, using the Siemens slower down to about 60 and then down to much lower velocities of, say, 0.5 meter per second or so, which is captured by a magneto-optical trap in the middle here. And then we modified the system such that we can then do interferometry by, well, initially we considered dropping these particles, but we're actually now driving them and forming a beam. And that's what I'll talk a little bit about. Okay, so this is the experiment as it stands at the moment. So this is Joel, who's actually doing pretty much all the experimental work here and running this system. So most of these optics here are for the magneto-optical trap. And you can see there's the Siemens slower, and you can't see the argon sign at the end there. But essentially, this is the science chamber where we create the magneto-optical trap and drop these particles or push them down, as I'll explain. And this is a close-up of that, and you can see at the bottom of this, perhaps if you've got good eyes, where the microchannel plate is, where we detect these particles.
What is the speed of the part?
Sorry?
What was the speed of the part?
Well, I'll get to that. It's adjustable, which is quite nice. So that's a slightly different thing that you can do with the atoms. So we have a cold stationary ensemble of these atoms to start with, in the order of 70 microkelvin and fairly large de Broglie wavelength, which I think is good for interferometry. So the reason why we use metastable argon is because these atoms are sitting in a very excited state. They're actually 11 eV above the ground state, so they have a lot of energy, and this is what makes them so detectable for us when we drop them on the microchannel plate. But of course, their center of mass energy starts off at sort of nano eV, which is useful for the interferometry. And the important thing is when they touch the detector, of course, they just ionize, and so we can detect one at a time. And that's really what makes argon and a few other species quite useful for these sorts of experiments. So as I said, we're essentially sitting up here, and we laser cool on this transition, and we have other transitions where we can. So essentially, when I talk about quenching, what I'm talking about is removing these particles from the metastable state where we can make measurements and take them down to the ground state where the detector is no longer sensitive. So we have that control as well, which is quite nice. So essentially, this is a magneto-optical trap. I've lost a. Oh well. You'll have to work it out, unless someone has a pointer. So what you see here is essentially it's a standard magneto-optical trap where we use 6 laser beams to laser cool this particle. And so originally, when we were thinking about doing this experiment, we thought, well, okay, what you see on the far side there with time. Different increments of time in a millisecond. If you turn off your trap, then, oh, thank you very much. Oh, well, have to focus. If you turn the trap off, then these particles drop, and so that can form your beam in principle. And I'll talk about that. That really wasn't suitable for us. And the reason why it's not suitable for us is because we just can't really get enough particles in here. So we have 1 million or 2, which sounds like a lot, But of course, it's because it's so cold, these particles are expanding, and so we only get to use a very small part. If this has to fall 20 centimeters, then we're only using a very small part of this beam. So what we decided to do, and actually this turned out to be good also for the weak stage, is that we need to get particles here so that we can see them from interferometry reasons, but also we need the particles to be not too slow traveling through the weak stage. Otherwise, the magnetic field that we require is kind of comparable to Earth's magnetic field, and it's not a position that you want to be in. And so for a number of reasons, we are now using this pulse source. So what we do is we take another laser beam, it's actually one of the same of those 6 laser beams, and we turn it on briefly and give this a push out of the trap. And so durations on the order of milliseconds will push these particles out of the trap, and then they travel down, and then they have enough velocity to do the experiment. So what we need to do then is to collimate this beam to reduce the transverse coherence, or to increase the transverse coherence so that we can do these experiments. And so what you see here is essentially a push beam, and you see these particles traveling towards the slit. And so what we can do now is we have this tunable source where so this is time, this represents actually in milliseconds the time that we use to turn on this source to give it a push. And so we can get velocities from the order of 10 meters per second up to about 30 meters per second. For this case, we can even go up to 100 meters per second, which then becomes more like a conventional atomic beam. Which we can't then do in the space that we have. So this is kind of a sweet spot for our experiments where we get enough particles through. And as you can see, with high velocity, you can see the particles don't spread so much, so you can see more on the detector, and if it's low velocity, then they spread out. There should be a value there, but there isn't. 10 meters per second, let's say. So the next step then is to do some interferometry, and that's kind of where we're up to at the moment. And so we have this beam, and just under this slit, we create an interference pattern, so an optical interference pattern, and this dipole force creates a phase grading for the light. So it's essentially this, and I won't go into that, but it's essentially the same as putting a slit there. Although the nice thing is, of course, that much more light, much more of these atoms can travel through that rather than a slit. We block off a number of them. So what we can do if we slit in, we can see this beam, and we can see that there is sort of the appropriate transverse coherence length for the velocities that we need, and we can dial this up. The only problem, so we were just sort of at this stage recently, and so this is what you get, and what you'd like to see there is an interference pattern, but what you see there is actually our mirror moving around, so we don't get a well-defined interference pattern. So that's where we're up to actually at the moment, but we soon expect to stabilize this system and to get a nice interference pattern, and then we can essentially start on the weak stage measurements. So as I said, we actually need to stabilize the system so that argon is very nice in that we can use it to detect single atoms, but the vacuum pumps we use are quite noisy, and so this means the system shakes around a little bit, so we need to fix that up. Also, if there's any spontaneous emission that occurs, then that can localize your wave function as well, and so you don't see any interference. That's not what we believe to be the problem is, but we have the option of actually moving to what's called, rather than red detune from the resonance, to blue detune, where we can minimize the spontaneous emission. And then we actually get to do this experiment where we can introduce this weak stage. And as I said before, we don't need to look at all of those M states. We can really look at the case where we turn off the magnetic field, and we can look at essentially no weak stage, and then look at this M0 state with the phase encoded in it. So there, whilst it's more of a challenge to set up this experiment, it's useful also because we have more control, for example, over the velocity and timing, so we can time parts of the experiment because the atoms move through so slowly. We can optimize it in other ways. So. It'd be about 150 microns apart, so they're well resolved with the microchannel plate. Yeah. So just in summary, so I presented the scheme for making weak transverse momentum measurements for atoms using this idea of spin polarization. And I've really shown you the setup that we have and the progress that we have to date and the work that we need to do. And what I would suggest, if you'd like to see more, then see the poster by Joel Morley, who's over there, who's been doing all of this work. And finally, just to acknowledge the Fetzer Franklin Fund for supporting this work. So thanks very much.